Hello students, we'll be working on the review for question 15 of our reaction mechanism tutorial. So in the earlier questions, you have seen some of the more difficult mechanism question, especially those from question 14, when you need to predict a number of steps and you need to have a little bit more experience. So question 15 will be a typical Cambridge examples where if you are required to draw a mechanism with quite a number of steps, we will guide you accordingly, or they will give you some intermediate structures. And you also notice that question 15 focuses on addition elimination mechanism, which is often something they like to test, and it's quite common. So very rarely will they be testing you something totally out of addition, elimination, or those which you are familiar with, such as nucleophilic substitution and elimination. So you can almost rest assured that the mechanism you're going to encounter will be within the framework of the curriculum. If not, they will guide you accordingly, just like some of the questions you might have done for H2. Okay, so without further ado, we'll take a look at question 15. You were told that there is a condensation reaction forming compound W from hydrazine as well as a diketone. So the structure of hydrazine is shown on the left. So this is hydrazine, so it's organic hydrazine. So it's a derivative of the usual hydrazine we are aware of, which is N2H4. And then the diketone is right in the middle. Okay, so you notice that in the intermediates, there is an CN double bond, or otherwise known as an imine double bond, formed between the N, which is the one right at the end, okay, and the first carbonyl carbon. So if I'm going to label the carbonyl carbon, this will be carbonyl carbon 1 and carbonyl carbon number 2. So basically, since the intermediate is already shown to you, right, then you would expect to draw the mechanism when you begin by performing a nucleophilic attack onto carbonyl carbon 1, and then probably perform an elimination of water molecule or something similar to give you the imine CN double bond. And then later on, in order to get W, then it will probably be another elimination reaction. So something along those lines. Okay, so without further ado, I think we can begin by drawing the reaction mechanism. Okay, so we will begin by labeling the lone pairs of electrons. Okay, so I'll just put a lone pairs in. Okay, so the lone pairs, you are not told the medium. Is it acidic or alkaline? So since you're not told the medium, then if you wish to use H plus to protonate the species like the oxygen, I don't think you should be using H plus because you are not told that the medium is acidic. Okay, so it will simply be a nucleophilic attack from the nitrogen onto carbon number 1. Okay, so we'll do that first. So nucleophilic attack, and then the pi bond will break. So this is the nucleophilic addition step. Okay, then in this particular step, I'm gonna have an R prime here, and then an O minus. Okay, so the rest will look the same, R double prime. Okay, and then I'm going to have an N here. Okay, with H, and then with the N, H, and then the R. Okay, so the nitrogen here will take on a +1 formal charge. Due to the fact that it is now singly bonded to 4 different groups. Okay, then you know that what you get here is a Zwitter ion, so you do expect some form of intramolecular proton transfer, okay, to take place. So you're going to transfer one of the proton over to the oxide. Okay, so and then the NH bond will be broken heterolytically towards the nitrogen to neutralize the charge. Okay, so with that, I'm going to redraw everything. Okay, and then the OH, and then double bond O, and then R double prime. Okay, and then N H, and H, and then R. Okay, something like that. Okay, then you might be thinking, how can we push towards getting the structure being shown in the intermediates? Okay, some of you might be thinking, what about an intramolecular proton transfer between the NH and OH lah? So maybe you might be thinking something. Okay, sorry, let me just. Okay, you might be thinking something like this. Okay, is it possible? Something. Oh, sorry, the ink is not working. Okay, you might be thinking something like this. Okay, my apologies, the ink is not working very well. Okay, something like this. Okay, no, this is incorrect. Yeah, because what you are going to end up with will be a super base, which is N minus, and in most situation, without any further information, right, the strongest base present, assuming that it's more or less an aqueous like medium lah with protonic hydrogen, right, it shouldn't be a base stronger than OH minus. Yeah, so we shouldn't be looking at something like this, but what we can look at is probably some form of eliminating the OH as a OH minus, because that is perfectly legitimate. Okay, because the reverse reaction will be one of nucleophilic addition. Yeah, so this particular step is perfectly fine. I mean, if you want to, you can just draw it in, and you notice that once you draw in this particular step, you are going to get your double bond N with a H, and then NH and R, and then my group will be lost as a OH minus. Okay, and then of course the nitrogen here will gain a positive formal charge, which it can easily be lost when the protonic hydrogen is being removed. It's being removed by what? Okay, so in this case, because I'm losing the OH minus, maybe I can draw the OH minus over here. Maybe I shouldn't put a minus. Okay, I just draw the OH minus. So the OH minus can be the one grabbing the H like this. Okay, maybe I should use a purple ink, I think, so that it's clearer, because I use a purple ink over there. Okay, so grab the H, yep, and then I'm going to get my intermediate R. Okay, so minus H2O to get my intermediate R. So R prime, and then double bond N, and then carbonyl group, and then R double prime, and then NHR. Okay, something like this. Okay, so that's the intermediate we are talking about, and then how can we continue to push all the way to compound W, which is a heterocyclic aromatic compound. Okay, you might not have learned that in the current H3 curriculum, but if you do a quick count, it has 6 pi electrons around the 5-membered ring. Yeah, in that case, it obeys the Harker's rule. Yeah. If chances arise, we can discuss a little bit more, but I think at this stage we will not touch on this. Okay. Right. So from here, what can we do? Okay. So the next step probably involve something similar to what we have drawn earlier on. Okay. So going to expect the lone pairs of electrons on N to perform a nucleophilic attack on the carbonyl carbon, and then I expect the CO pi bond to break towards the oxygen. Okay, something very similar to what we have earlier on. Okay, and then I'm just going to continue. Okay, so you will notice that when this happens, the ring will kind of close up. Okay, so because the ring sort of closes up, then I think we have to reorientate this a little bit. Okay, so I'm going to have an N over here, and then I have a H, and then an R group over here, and then this is going to be R prime, and then I'm going to draw this in, and then there's a R double prime, and then of course I have a O minus. Okay, and not to forget the nitrogen will gain a +1 formal charge. Okay, and then this serves as a good opportunity for an intramolecular proton transfer in order for me to neutralize the charge at the nitrogen, and at the same time to create a possible leaving group so that it can leave. Okay, yeah, so when this happens, you notice that we are getting closer and closer to our answer. Okay, so I'm going to draw this in quite quickly. Okay, and then this is R double prime, and then we have a OH here. Okay, and oops, I think I drew the groups a little wrongly. Okay, so let me just I'm just going to erase this portion. Okay, I think this is drawn slightly wrong, incorrectly. Okay, like this. Okay, so this is R double prime. Okay, yep, so we're going to do the same thing. I'm going to form the pi bond. Okay, because remember that we need to form another CC double bond, but at the same time the lone pairs of electrons on this particular nitrogen needs to be regenerated. Okay, so first I'm going to form the pi bond and kick out the OH minus, which we have done earlier on. Okay, so we're going to do that, and then I'm just going to draw in the R prime. Okay, and then double bond and R. Okay, and then like this. Okay, and then R double prime. Okay, and then this will take on a positive +1 formal charge. Okay, and then what's going to happen next is that the OH minus, okay, so the OH minus lost, okay, will then grab the proton here, because this proton is likely to be acidic, and I have an electron sink at the nitrogen bearing the positive charge. So what's going to happen is that you will grab this hydrogen, and then I will form the CC double bond, and then now the pi bond will break towards the nitrogen to neutralize the charge, and that's how I end up with W. Okay, so I'm going to zoom out for you to take a look whether we have successfully produced W. And then you notice that in the course of the reaction, 2 equivalent of H2O is being lost. If I'm going to highlight the H2O, one equivalent comes from here, and another equivalent comes from here. Okay, so I think everything is is well produced, and nothing is being I think none of the steps is controversial. So if you are able to propose a mechanism like this, you are likely to be marked correct for your Cambridge exams. All right, okay, so with that, we'll just move on to part B. Okay, so for part B, we were told that unsymmetrical diketone can give a mixture of products. Yeah, so of course, in order to get X, X will attack, or rather, in order to get X, right, the nitrogen on the hydrazine will attack carbonyl carbon 1 first. Okay, in order to get Y, the nitrogen will, the nitrogen with the lone pairs of electrons on hydrazine, right, will attack carbonyl carbon number 2 first. So for this particular question, we were asked to consider both steric and electronic effect. Yeah, these are very two important terms which I think I have highlighted to you countless times from our learning objectives in our syllabus. I think the one I mentioned is in the H2 curriculum, learning objective 11.1c, when the students need to be able to use steric and electronic effects, including withdrawing and donating groups, to skillfully navigate between explaining why certain reaction happens the way they do. Okay, so with that, you should also be aware that this is also required of you in H3 curriculum. In fact, it is a more important aspect of H3 curriculum. Okay, so now you are asked to consider both steric and electronic effects in the key step in mechanism in A. So again, they kept it open in the key steps. So depends on how you interpret the key steps. But I do interpret it as the nucleophilic attack in the first step in carbon number 1. So that should be the key step. Yeah. Why is that the key step? Because that will be the step that which determines whether you get X or Y. I hope you agree with me on that. Okay, so I'm supposed to consider the steric and electronic effect in the key step, predict which of the two products will predominate. Okay, yeah, so this become a relatively H2-ish kind of question. Yeah, so okay, so number 1, right, if I solely look at steric effects, okay, I will expect X to predominates. The reason why, if we look at steric effect, we expect X to predominate is largely because the phenyl group is a larger group than methyl. Okay, so maybe I will just impose a greater steric demand than methyl. Okay, yeah. So if we look at steric effect alone, then the nucleophilic attack on carbonyl carbon 1 will be preferred over carbonyl carbon 2. Yeah. If we look at electronic effects alone, okay, electronic effects, I would expect X to be the dominant product as well. So you'll be wondering why lah. Okay. First of all, we need to ask ourselves, right? Why nucleophile attacks carbonyl carbon? Okay. The reason is carbonyl carbon is electron deficient. Am I right to say that? Okay, so carbonyl carbon is electron deficient. So therefore, carbonyl carbon is susceptible to nucleophilic attack. Yeah. But right now, both carbon 1 and 2 are carbonyl carbons. Yeah. So I think the decision we have to make is which of the two carbonyl carbon is more electron deficient. Okay. If we can answer that, then I think the answer is obvious. Okay. Now, if you take a look at carbonyl carbon 1, right? Let me just highlight. Okay, this is a methyl group. This is essentially a CH2 lah. Okay, so essentially it's an LQ group. Yeah. So I would expect inductively, right, both of this group, right, to be able to donate electron density inductively towards the carbonyl carbon. Carbonyl carbon 1 for that matter. Okay, so that will make carbonyl carbon 1 maybe less electron rich than, for example, formaldehyde, when both the groups are H's. Okay, but we're not comparing with formaldehyde lah. We're comparing with carbonyl carbon 2. Okay, so for carbonyl carbon 2, right, I do expect this CH2 group, right, the methylene group, to also donate electron density to carbonyl carbon 2. Okay, what about the phenyl ring? Okay, so phenyl ring is quite interesting. Okay, so I'm just going to sketch out the phenyl ring over here. Okay, so if I have a phenyl ring, right, you'll notice that it has unhybridized p orbital, which forms a continuous overlap of pi electron club. Okay, and then next to it, right, I'm going to have a C double bond O, which also has a pi electron club, and then the rest will be blah blah blah. Okay, so the rest I don't really care. Okay, now CO group is electron withdrawing. Okay, we all understand. And I have a large pi electron cloud conjugated to the CO group. So what do you expect the pi electron cloud to react? You expect the electron density, right, over here to be pushed towards, to be withdrawn towards the carbonyl oxygen. Yeah, so when the electron densities, when the pi electron densities is being withdrawn towards the carbonyl oxygen, it makes carbonyl carbon 2 less electron deficient as compared to carbonyl carbon 1. So it reduces the electrophilicity, or okay, we say that carbonyl carbons are electrophilic in nature, right? So both 1 and 2 are electron deficient or electrophilic. But carbonyl carbon 2, right, is less electrophilic as compared to carbonyl carbon 1, solely because the CO double bond, right, is able to withdraw the pi electron cloud electron density towards itself. So it makes carbonyl carbon 2 less electron deficient. So therefore, carbonyl carbon 2 is less susceptible to nucleophilic attack as compared to carbonyl carbon 1. Yeah, so because of that, I will expect X to be the dominating product. Okay, so I'm not going to write out for you. You can decide how and write it out yourself. But most importantly, you need to address these 2 points, both steric and electronic. They are not asking you to just focus on 1 point. Okay, so in the Cambridge exam, I think this question is worth about 3 marks if I'm not wrong. Okay, so I think you really have to ensure that your answer is worth some salt. It has to be quite a strong response to the question. Okay, especially the electronic effect portion. Okay, next, we take a look at part C. Suggest the starting material in this case hydrazine and diketone, I think you have to take reference from A, needed to synthesize the drug celecoxib via this reaction. Okay, yeah. So I don't think I need to discuss too much on this, because I think you guys are quite good at deciding. Okay, so basically the hydrazine will be this whole portion. Okay, this is the hydrazine, and then the diketone will be over here. Okay, yep. So if I'm going to sketch out, I'm just going to say that the hydrazine, okay, will be like this, S double bond O, and then a phenyl ring, okay, and then after that NH and H2, okay, and then I will also need the diketone. So the diketone will be the trifluoro, okay, diketone, and then a diketone here, and then a phenyl ring, okay, a phenyl ring, and then a CH3, okay, a CH3, something like that. Okay, yep. Then the final parts, which some of you might remember, in the tutorial, quite a number of you have issues in coming out with the structure of Z, because you don't know how to decide on the carbon anion. Okay, so another derivative of W can undergo halogenation, okay, removal of proton. So that means that protonation is required, and then because protonation is required, we have to consider the stabilities of the carbon anion intermediate, and then from here we need to predict the product Z. Okay, so I think first of all, right, we have to decide where are the potential sites the proton can be removed. Okay, so if I'm going to sketch it out, so there are 3 potential protons. One of them is A here, which is HA. The other one is HB, and then the other one is HC. Okay, so shall we just draw all the 3 outs, all the 3 carbon anion outs, and then from there we can decide which is likely to be removed. Okay, yeah. So I'm just going to draw the first one out, like this, and then this is the carbon anion with negative charge. Okay, then versus the other one, pH, double bond N, double bond, and then N here. Okay, and then with a lone pairs of electrons, and then versus the other one, which is this. Okay, and then N, and then with a lone pairs of electrons here, here, and here. Okay, so maybe I should draw the double bond more clearly like this. Okay, first of all, right, we need to identify the electron sink, which is essentially a C double bond O equivalent. So I'm just going to highlight. So this is an electron sink here, is a C double bond N. Okay, so remember that if I have a carbon anion, right, ideally the negative charge should be delocalized over to the electron sink. Okay, if not, then you might as well not get the proton removed, because the structure is not likely to be stabilized. Okay, so if we try to do that, you can argue that, okay, this lone pairs of electrons being found in the p orbital, right, I can push electron density like this. Okay, I can push to the carbon. But have you ever wondered, right, if you push to the carbon, isn't it quite the same, because carbon and carbon have similar electronegativity values? Yeah, so if that is the case, then why will you say that the lone pairs of electrons is delocalized? Maybe it's a conjugated system, yes, with a C double bond N next, C double bond C next to it, but it's not going to give it a lot of stability, and you cannot even push it over to the phenyl ring, because you notice that there isn't a C double bond here. Yeah, so again, you are kind of like stuck. Okay, so this is the best way you can do it, which is okay, but maybe not so stable. Okay, well, if you look at the second one, right, you'll notice that I can push the lone pairs of electrons all the way to the electron sink. Okay, I can easily draw out a resonance structures very nicely. and it's a stabilized one. Okay, because I can push the electron density all the way to the sink. Okay, and then this is a double bond. Okay, and then the N here, and okay, with a lone pair here. Okay, and of course there are two lone pairs we are talking about with a negative charge. Okay, so this seems to be the one which we are looking at, so I'm going to put a smiley face. Okay, what about the third one? Again, the third one is not possible because there's a lone pair here, not to forget. So I can't push this in, because if I push this in, then the number of electrons around the nitrogen center will be 10. Yeah, that means something has to be pushed away, right? So what can be pushed away? It's the sigma bond have to break. But breaking of sigma bond means it leads to fragmentation, which is obviously not desirable. Yeah, so therefore this should be the most unstable one, and we should not even consider it. Okay, then with that, are we able to draw out the mechanism? Yes, I think we can do that, because in the presence of OH minus, what you can do is you should be able to push the electrons all the way into the electron sink. Okay, so I'm going to show like this. I grab HB, okay, then the CHB bond will break heterolytically, and then I push all the way to the electron sink, which is the C double bond N. Okay, then after I've done that, this is what I will get. Okay, I'm going to get this. Okay, and then what happened next would be the bromine will undergo electrophilic addition. Okay, when I push back the electron densities, I push, and then the Br bond will break. Okay, so eventually the products I'm going to draw will look something like this. The phenol ring, okay, and then N, okay, and like this, okay, and a Br over here. Okay, so this will be the answer I'm looking at. You might want to check out whether it satisfies the molecular formula. So yes, there are two nitrogen, there's one bromine. The number of hydrogen will be, the methyl group here will have 3 hydrogens, so 3, and then over here we'll have 2, so 5. Over here we have 3, so 5 plus 3 is 8. 8 plus 5 in the phenol ring is 13, so the number of hydrogen matches. What about carbon? Yeah, so in the 5-membered ring there are 3 carbons, plus the 6 carbon in the phenol ring, so that's 9. And then in the side chain, I have 3, so 1, 2, 3, so 9 plus 3 is 12. Yep, so this will be the answer, and that's it, right? That's the end of our review to question 15.